alright. What is the simplest way of or rather I would say what is the dumbest way of doing this? The most straightforward way of doing this is to say, well, we knew we will write Kirchhoff's law again. So now what happens? In the earlier case, remember that Vi was nothing but Vt ln I over Is plus IR2. Okay. In the circuit on the right, what do we see? Vi, we do not know what the current will be. So, the current is I, it is going to change from before plus delta I, and so therefore Vi plus delta Vi must be equal to the diode voltage plus the drop across the resistor. What is the diode voltage? Vt log of I plus delta I over Is plus I plus delta I times R2. Correct? What is the most straightforward way to do it? Is to say, well, we solve this numerically. So now we have changed the input voltage. So, well, you go to the computer again and solve for this. So this new delta I, and then for this new I, which is different from the earlier current, and find the new output voltage. Does that make sense? Okay. Now this will work for an arbitrary change in the input voltage, correct? But now if I told you that delta V is small, what is the first question that you should ask me? Small in relation to what, correct? But at this point, we will revisit this question later, but at this point we will assume that it is small in some sense, okay, or in the right sense. What that sense is, we will come back to later. So if that change in the input voltage is very small, then intuitively what do we recognize? We have already solved this problem where the input is so close to our current input, okay. Now the question is, does it make sense for me to go and do all that hard work all over again, or can I exploit the fact that I have solved a problem which is this close to this problem? Perhaps I can exploit the fact that I have done a lot of hard work already. Can I use the results of that to solve my new problem? Does that make sense? Now, so how do we figure this out? Well, if you look at this equation, let us call that 1, and if I call this 2, what does 2 minus 1 yield? 2 is valid, 1 is valid, right. So what does the difference between the two yield? On the left hand side you have delta Vi, and this is nothing but Vt ln I plus delta I over I plus delta I times R2. Quick question, is this valid for all delta Vi, or is it only valid for small delta Vi? There is nothing wrong with this equation. This is valid for all delta Vi, because both equations 1 and 2 are valid for all values of excitation. and I have simply subtracted the two equations. Now, if delta Vi is very small, so in other words, if the exciting input has changed just a little bit, right, where again we will come back to what this just a little bit means going forward. If this delta Vi has changed by just a little bit, what comment can we make about the change in the loop current? The change in the loop current will also be very small, right, so under those circumstances, what can we, so remember that this is therefore ln of 1 plus delta I by I, and if delta I by I is much smaller than 1, what comment can you make about this guy? Ln of 1 plus x for mod x much less than 1 is what? I mean, ln of 1 plus x for x equal to 0 is equal to 0, right, but for small x where x is very small compared to 1, what is it? 1x. People, 2 years of COVID has wiped out your memory also, huh? Y is equal to x. Yes, no? All right. So, the ln of 1 plus delta I by I is what? Delta I by I. Okay. So, now what does this equation reduce to? So, 2 minus 1 gives you delta Vi is Vt delta I by I plus R2 times delta I. Fair enough? Okay. So, now tell me what is known and what is unknown. Let us start from the left hand side. Delta Vi is known. Is Vt known? Yes. Is capital I known? Where? Oh well, yeah, we had already solved that problem by working hard. So, that is known. What about delta I? Delta I is unknown. R2 known, delta I is unknown. So, this is also one equation in one unknown. However, what is the big difference between what we did last time and what we are doing now? This is a linear equation in one variable. So, presumably it is a lot easier to solve than solving a nonlinear equation. So, this basically means therefore that delta I is nothing but delta Vi divided by Vt over I plus R2. Okay. So, what comment can we make about the total current now? So, earlier when we had excited the circuit with Vi, we got some I. Now, when we excite the circuit with Vi plus delta Vi, you should get I plus delta Vi by Vt by capital I plus R2. Okay. What are the dimensions of Vt over capital I? It's got dimensions of resistance, okay, and so therefore the bottom line therefore is that if we have a nonlinear circuit, to find the the branch currents and the branch voltages for an arbitrary excitation is fundamentally a difficult thing to do, right, as we have discovered even with our simple diode example, right. Okay. And you can imagine that even with this when even with this simple example we found that we had to solve a nonlinear equation in one variable. Now you can imagine what happens if you have, say, a network with I don't know 10 nodes and multiple nonlinear elements. What will we end up having to solve? How will you solve it? If you have a more complicated nonlinear network, how would we go about solving it? I mean, MATLAB is just a tool, right? So, what are you going to feed into MATLAB? What did we do here? No, what did we do here? What did we plop into MATLAB? Yeah, we basically wrote KVL / KCL equations and dumped those equations into a nonlinear solver, right. Now, if you have 10 nodes and a lot of nonlinear elements, what comment can we make? What will you do? You write all the the KCL equations at every node, correct, and now unfortunately because the elements are nonlinear, what comment can we make? The branch voltage is related to the branch current through a nonlinear relationship. So, you will get a system of nonlinear equations and these are all coupled, correct. Okay. So, you will now get a system of nonlinear coupled equations in the variables, and solving even a single nonlinear equation is seems to be very difficult. So, you can imagine how it would be to solve a bunch of nonlinear coupled equations. So, what do you do? How would we solve it then? Well, you just like we did in the simplest case, we will take the system of equations into your favorite mathematical tool and solve the equations numerical. Does it make sense, people? Yes. Right? What we are doing for the simple one, we will do for the more complicated one, except that now we have more variables and more equations, and the equations are also, because there are more variables, they are also coupled, right. So, for example, if you put a diode between two nodes, the current flowing through the diode is exponential of V1 minus V2 by Vt times Is and all that stuff. Okay. So, you can imagine that, as you can probably imagine, the solution to these equations becomes finding it analytically is almost impossible. You have to resort to what do you call some kind of numerical technique. Okay. However, as we have seen in this particular case or this particular example, if the excitation changes by a small amount from the previous excitation, what we are seeing is that we do not have to do all that hard work all over again, right. One can actually leverage the work you have done in the for the previous example, where you found all the voltages and currents for a given excitation, right, and from that it seems a much easier job to find what happens to the branch currents and the node voltages when the excitation is changed by a small amount. And in this particular example, what comment can we make? What qualifies as a small excitation? Look at where we have made the approximation. So, basically any excitation where delta I by capital I is much smaller than 1 is within quotes so a small signal, a small excitation or a small change in the input is defined as that which results in a change in the loop current, where the change is much smaller than the current I, and that pertains to this particular example, right. In general, each circuit or each nonlinear element will have a different definition for what it means for the excitation to be small. In this particular context, it just so happens that the delta I by capital I must be much smaller than 1. All right. So, so this delta, now some jargon, this delta Vi, capital Vi is to avoid having to write capital delta and capital V, it is often written in small case, right, and this is what is called the small signal or the incremental quantity. Okay. Capital Vi is what is called the quiescent quantity, whether it is a voltage or current or whatever, right. In this case, because Vi is capital Vi is a voltage, it is called the quiescent voltage, okay, and the capital I is the quiescent current. Sorry about the and the small I is the incremental current. Does that make sense, people? So, so in terms of our new jargon, we can basically say that if that incremental excitation is if it qualifies to be a small signal, then after subtracting the equation 2 from equation 1, we basically get Vi, which is nothing but Vt by capital I times small I plus small I times R2. Okay. And once you have an equation like this, once you have a linear equation, you can also have a circuit which represents this linear equation, all right. And what is that circuit, do you think? What is it? So, the source is replaced by the small signal equivalent, all right, and what happens to the nonlinear element? It is replaced by a resistance capital Vt by I, and what comment can you make about the resistance R2? And what is that voltage? Small Vo. What is the current there? Small. Okay. And to find small VO is as straightforward as finding the output of a resistor divider, and as you can see, the small I is simply nothing but small Vi times R2 by R2 plus capital Vt by I. So, so for small signals, therefore, we have replaced the nonlinear element, in this case a diode, by a linear one, right, and the what are the properties of the linear element? What does the value of that resistance depend on? I mean, Vt of course is is a given at a given temperature, right? It depends on the quiescent operating point or the quiescent current. Okay, and this is often also called the small signal resistance of the diode. Okay, and okay. Now, in general, therefore, if that nonlinear element, let me quickly go through this. Let us generalize. Let us say you had a network with capital Vi, some nonlinear element and some resistance R, and let us say this current or this voltage was some function of the current flowing in the network. Okay. What comment quickly, what comment can we make about the output voltage VO? How do we find it? Pardon? Okay, no, there is no increment here. This is just I have applied a voltage to a nonlinear network. How will we find VO? KVL. What does KVL give yield? Vi is nothing but that is some function of I plus I times R, and then you solve this numerically. Find I. That makes sense? Now, if I add a small signal, the current changes by a small amount and the output voltage also changes by a small amount. So, what do we say? Vi plus small vi is nothing but f of capital I plus small I plus I times R. Sorry, I plus I, thank you. Very good. Now, how will you relate f of capital I plus small I in terms of capital I? Use the Taylor series. So, in general this is nothing but f of I plus small I df over di, where I abuse notation a little bit. What I mean is, when I say df by di, is the derivative of the function with respect to its argument evaluated at capital I, right. Okay. And just to make this clear, I will write that as okay. And what should be there? Small I plus second derivative, okay, times I square by 2 factorial plus third derivative I cube by 3 factorial and so on. Does it make sense, folks? Okay. Now, if that current is if the change is very small, what comment can we make? How can we approximate this f of I plus delta I? Yeah. So, basically we take only this and neglect higher order terms in the Taylor series. And the intuition is that, well, if you have a curve and if you are looking at if your point about which you are expanding is that, then around that operating point, okay. So, if you are sufficiently close by, you just need the slope. If you go too far away, then you need curvature and all that stuff. Okay. So, now so therefore, what in general what qualifies as a small signal? When will this be a good approximation?
When the I is such that I is not changing much.
In this Taylor series, when is this a good approximation?
Change is not much.
So, basically when your approximation is good, right, and this is the complete series is the true thing, right, you are trying to approximate it by just the first two terms. So, obviously the approximation is only valid when df by di times I in magnitude is much greater than all the higher order terms. This is the true definition of what it means for a signal to be considered small. Okay. So, this is the definition of what constitutes a small signal. And what does this depend on? As you can see from this equation, what all does this depend on? It evidently it depends on the function. What else? It depends on what? It depends on f, it depends on, it also depends on remember we are, I mean all this is basically saying that we are evaluating the derivatives where? At the quiescent operating point, correct. So, it not only depends on the function, even for a given function it depends on the operating point. Okay. Does it make sense, folks? Right. For instance, let us say you had a function like this, okay, and you are operating, this is your operating point 1, operating point A, this is your this is your operating point B, right. And let us say I have a fixed increment around both these operating points. At which of these operating points will the notion of small signal be larger? Which signal will count as a small signal, or rather there is obviously at each operating point there is a limit for what constitutes a small signal. For which of these operating points A and B will that limit be larger? A. Why? Well, A looks like a lot more linear, and whereas B the thing is curving like this. Okay, so clearly you can see that this definition of small signal is not absolute, right? It not only depends on the device, but also depends on the operating point for that particular device. Okay, so it's very context dependent. It is not something absolute, right? And a good case in point is the diode, right? In the reverse bias region, what comment can you make about the operating? I mean, what constitutes a small signal? You can see that the curve is virtually flat. So, a small a large change in the applied voltage will result in expected to result in a linear change in current, with that proportionality constant is close to 0, correct. Whereas in the forward bias region, you can see again that it's exponential. So, we to evaluate what constitutes a small signal, we have to find the higher order terms of the Taylor series, compare it with the first order term, and then basically you understand. So therefore, let me just finish this topic. So what comment can we make when we subtract these two? What do we get under the small signal approximation? What do we see? Let us subtract the first equation from the second. What do we see? Small vi equals df by di small times small I. Yeah, df by di is it's understood that it is abuse of notation, but it is understood that it is the derivative evaluated at capital I plus r times small I. All right, and therefore equivalently, if you want to draw a network which models the difference between the two equations, this becomes a linear resistor with a value df over di and a resistance R, and this is small vo, and therefore small vo is nothing but vi times capital R by capital R plus df over di. Does it make sense, people? Okay. All right. So, tomorrow we will continue. Thank you.